So the first thing that you do is read the question. And when you read the question, look for the physical terms. And the most important term in this question is when it arrives at B, the rope is barely under tension. That's the most important word. So that means when it gets to this point, look at the screen please. When it gets to this point, there is no tension. Correct? If there is no tension at this point, then the only force is mg. And so mg should be equal to the centripetal force. If you write that just now, write it. mg is equal to mv squared by r. The masses cancel out. You will get the velocity at that point. That makes sense? Once you get the velocity at that point, you go to, okay, we have to use the principle of conservation of energy. So take this as the ground. This is the ground. That means it has no potential energy at that point. It only has kinetic energy. But when it gets to this point, it has both potential and kinetic. Correct? The total must be the same. So that's why when you look at this, you see that the total energy at A is equal to the total energy at B. Yep, I'm writing all of it just so you see that, but you know that this quantity is going to become 0, right? Because I picked this as the ground, so you only have this quantity. And then plug in, the height is 1.6, and the masses cancel out again, don't they? And you would calculate and get that step. So I stopped there because I said, okay, we are trying to find this velocity, but we do not know the velocity at B. Do you see that? That's why I asked you to first find the velocity. So I told you at B the tension is 0. So the weight is the centripetal force. Rearrange that. You get the velocity, plug it back into this equation. You get the velocity at A. That's how you solve that question. So yes, there are 2 steps in it. The first and the most important thing was for you to realize this. I'm quite sure many of you did not even see that. At B, there is barely any tension, means there's no tension. That's where you start. A small toy car is released from rest. Okay, that's important. It has no kinetic energy there. And if it is released at a height 2r above the floor, how high is it above the floor when it leaves the track? Okay, so it's going to go, and somewhere along the line, it's going to just drop off. You see that? It's not going to complete the loop, if you know what I'm trying to say. It's going to go, follow the loop, and at some point, it's going to lose contact. Again, when it loses contact, the normal reaction, tell me, 0. Because when it loses contact, it's not pressing against that surface anymore, is it? So that was the key again. The normal force is 0, and you're asked to find that. Once again, it's the conservation of energy. And you will see how I'm going to work it out. But first, you have to draw the forces here. There's only one force in this case, which is the weight acting vertically down, which is mg. Right? I already told you the normal force is going to be 0, but I'm going to show you that normal force, possibly. There it is, but it reduces to 0. Now, I took the component of this weight towards the center. Do you know why I did that? Do you know why I did that? Because now I know what the centripetal force is. What's the centripetal force? It's mg cosine theta. Does that make any sense? Because the weight is acting vertically down, I took this component, which is going to be the adjacent side, so cosine, set it equal to the centripetal force. Again, n is 0, remember? So cancel the mass, get cosine theta, and then go back to that triangle, and I'm setting up that little triangle. I drew it again. I'm calling this height h. So that height is from the center, isn't it? You can see that here. Height h, and what's that? What's that? You're not with me. What's that? The distance, I mean. The radius. So this is the theta. So it's going to come up. So again, cosine theta in that little triangle is h by r, isn't it? Isn't it h by r? So I get another expression for cosine theta. Now what I do, since the left-hand sides are equal, I'm going to put the right-hand sides equal to each other, get rid of the radius, get the height, plug in the numbers. I got the height in terms of velocity, right? Now don't you know that the potential energy at A, what am I trying to say, is equal to the potential energy at B plus the kinetic energy at B, isn't it? Same thing, conservation of energy again. Why did I get it as mg times r? Anybody? Because I set the ground at the middle there. Remember that. That's why the height is the radius. Okay. Okay. For the h, I substituted as v squared by g. Do you see that there? Right. That's all I do. And then I cancel the mass. But that's the height from the center, isn't it? So don't I have to add the radius to get the total height? So add from the ground, it would be 1.67 times the radius. In this question, it's a free body diagram. What are the forces that act? Weight? Is there friction? Yeah, so friction would be straight down, right? So mg and then the force. You will have to break all of them into the x and the y components. I'm going to first show that with the applied force. I think I'm calling it FA. There you see it coming up. So the applied force is FA. Those are the two components, FA sine theta and FA cosine theta. And then the weight is coming up there, mg. Then you see the friction, don't you? Friction. And then break the weight into two components. And net force, take the net force along the x and the net force along the y. I think I've not shown the normal force. I'm supposed to show the normal force up. So the net force along the y. Is that correct? If the normal force is up, these two are down. So I add it down, see? Along the y. Now it's just a matter of plugging in the numbers. Theta is given, so I get that. Friction is mu times Fn. So I substituted the whole value of Fn here. So to get mu times that for friction. Then I go to the, that's the maths, just distribute that. And then the x-axis. On the x-axis there are how many forces? Fa cosine theta, up, isn't it? And there is friction down, come on. Yeah, so, and mg sine theta. So there it is. That's along the x-axis. And you have to have a lot of focus to be able to do such problems. You have to remember that we're looking for FA, so keep that as the subject. And then there is, of course, math in here. You have the two equations, you can easily solve them to get the applied force as 83.5 Newton. At least read this question and tell me, is it going down or up? Yeah, because there are three choices down. Is that why? No. Because if it's not moving, how much would the scale read? 60 times 9.8. How much is that? 588? Yeah. But now it's only reading 400, so it's reading less, so it should be going down. So at least we know it's going down. But then you have to draw the free body diagram and then calculate. You can't go by assumptions. Now from the free body diagram, this is what I'm going to get. I thought I had drawn the free body diagram. How would the free body diagram be? N would be up, mg would be down, and A is down, correct? A is down. So you have to be careful. You have to, if you write it as mg minus n, it's equal to ma. Mg is down. Mg minus n is equal to ma will get you back to this relation. And then substitute into that. I should have drawn the free body diagram for that. I was so upset, so I just went, no, I'm just doing it. But you understood, didn't you? I don't know. Did you? Oh, can't even draw it straight now. Holding everything like that. So this is N, this is mg, isn't it?
Yep.
And it's going down with A. That's why I said mg minus n is equal to ma, which will get you to this. Hope you're getting it. You want to cancel out the sum of these three forces. So first you find the sum of the three, and then you put the exact opposite of what you get. Isn't that what you do?
Yeah.
That's your idea. So to add them, isn't this actually 4i plus 4j? This is what? Minus 2i plus 3j. And this is minus 3i minus 2j, you know. So write that, and then it's nothing. This is like 4 points giveaway. What do I see? I see people make a mistake on that. F1, F2, F3, call it in any way you like, add them. And, that is too slow. Okay, add them. When you add them, you would, I think I wrote something wrong. I changed it now. Yeah. So that's what you get, and then you take the exact opposite of the resultant. It's called an equilibriant, and it's I minus 5j. How many understood? Oh, good. Thank you.